This video is supported by the National Science Foundation.
Hello and welcome to part 2 of our series on deep learning for IC reverse engineering. In our second part here, we'll be working with actual SEM images or an IC reverse engineering dataset. And our task will be to predict which layer is present in the given SEM image. So here in the first part, we sort of skipped over how do we load data, how do we implement our own data set, and that's what we'll focus on a little bit more here in the second part. So we'll implement our own data set subclass, and then we will use our simple CNN. We'll start off with that simple CNN to train the model and see if we can predict, and then see if we can improve performance a little bit more. And we'll do the similar classification analysis of the score predictions and the confusion matrix as well. I've also included some links here to an overview of deep learning models. It's in the link will also be in the supplementary materials. And this article just has a nice sort of overview of a bunch of the model zoo or the architecture zoo of different AI models. And then there's a great site, the CNN Explainer site, that has some nice visualizations to build the intuition more for what a convolutional neural network is doing and the computations associated with it. So our classification task is to predict which design layer is present inside of these SEM images. So we'll have 3 different layers: the doping layer, contact layer, and the meta layer. And we have these sort of noisy grayscale images that we want to see if we can train the CNN to quickly detect and quickly classify which layer is present. And we'll see how well we can do. So let's jump into the code. Back in VS Code now. I've already set up my imports a little bit, and I've added this part2.py file to my working folder. And just as a reminder, we have this data folder, and this is the CFAR images where they were downloaded from part 1, and we have our SEM images folder here, which has each split, the test split, train split, and validation split in each of it. Inside of it, which inside of each split folder has a folder of images and the mask labels that are associated with it. So these labels are the raw mask information. So this is what the ground truth mask is, and this in each image is the sort of the SEM image for that mask, right? So this is the noisy version of those images that are SEM. So just to kind of have that folder structure in mind as we're working through this here. On this cell first to open up an interactive session. And let's start implementing our data set. So the first thing we need to do is subclass the torch utils data set class, which is torch.utils.data.dataset. We need to implement 3 important methods. The first is the initializer. The second is the len function. And the last is the get item. So these are the 3 methods that are necessary to subclass dataset. You can have other methods on there that are helper methods or all kinds of things that you need to do if you need to do extra computations for your dataset. But bare minimum, you need to have these 3 implemented so that PyTorch, when it's using these data sets, knows how many samples you have, the length of your data, and can index into your data set to get samples. And then the initialization for initializing it with any particular parameters or characteristics for that data, which we will leverage. So to get started, let's implement our initializer. We're going to need to know where does our data exist? Where's the root path to our data? We will want to know the transform that we're using to transform our images. Are we going to resize those images? Are we going to do any other transforms to it? And then we are going to also set which split we're loading. So this is how we'll control whether we're loading the training, validation, or test split. And I'll just take an index, or I'll just take the string train. I'm just going to reformat it to make it easier to see. And then I'll just set those properties on my class. Next, I will collect the image files that are in my data set. And then sort that so that I have some consistency across initializations, where the key is I pass in a lambda function So this will sort that image files list, and I'll sort them based off of the file name, the stem, with the file name without extension. And I will get my labels. I'm actually going to derive my labels from my file names. So our file names, if you look at the top here, the first part of the file, if I split this based off of the underscore, the first part is an ID. The second part is the layer that it's associated, or the design layer. So this is the contact layer image. And then this is just the type of image that it is, the SEM image. We can ignore that second part, but we're interested in this CO here, which is our label. That is the label of our image that we want to use for this task. So I'm going to write a helper function that takes in a string, takes in the file name. Now, this label, though, is a string, and I want to map that to an integer, because that's what I can work with in PyTorch. So I'm going to write another helper that is an ID to label dictionary. This is just going to be a static property on the SEM images dataset. So that is my lookup from index to string. And then I also want, I'll write a static method where this is the label to ID. So then if I go back down to my labels, I can combine all of this to iterate in a list comprehension. I can say self.get. And then instead of returning the string label, I'll use my lookup, SEMimages.dataset, label to ID, pass in that label, and that should return my int. That little extra type annotation. Now I can quickly implement my length, just as simple as return the length of my self.images image files. So I now have a mapping. All of my image files in my dataset, I have sort of the paths to those files, and I have all of the labels where the indices into my labels and the indices into my image files are mapped, or matched. Now that we've implemented our data set, we have implemented all three necessary methods. We can return the labels and image tuples. So let's instantiate our data sets. I'm going to resize our images to be a little bit smaller. I believe they're 256 by 256 now. I want to make them half size just to make the training a little bit quicker and to take up less memory on the GPU. So first thing it'll do, it'll take in that pill image, resize it, and then turn it into a tensor and change the order of the channels so that we have a proper batch channel height width. And then instead of doing individual variables for our data sets, I'm actually going to create a dictionary for data sets and a dictionary of our loaders. And then I can iterate. And I'll print out the data splits. So I'll iterate over the data sets and just print out the length of each data set to see what we have. If all goes well. Oh, I don't think I ran the actual definition yet, did I? So I'll rerun that to define our class. I think we're getting that error because it's not finding the images. Aha, I forgot to add the split. So our full path is actually the root path, the split, and then images. And run that again. Need to get rid of self there. And this needs to be split. Silly. There we go. So we can see after those little mistakes, our training data set has 2,000 images in it. Our validation has almost 300, and the test has almost 300 images in it. And just as sanity check, we'll also include our training distributions. And we can see for our training data set, we have a fairly even class distribution. I can change this to val real quick. See for validation, about the same, and test. And so we have a little bit of a difference, but for the most part, again, this is our curated data set. So we have a fairly well-balanced number of representations for each of our classes. Some quick visualization code. So We can see here are the first 8 images or so in our training data set. And we can even just keep running this, and we'll get the next batch. We get a different batch each time. And so we can quickly kind of scan a couple of the different samples to see what we have. We now have our data working. We have all of our split loaders and data sets ready to go. So let's grab our simple CNN model from part 1. So I grabbed that entire code, all that set of code. And I think we'll just start off with this particular implementation first and run our training on that. Let's clean this up a little bit first. Let's just initialize our model and make sure it's still kosher. And so now in this case, we need to set our image shape to be not a color image, but a grayscale image. So it has one channel. And I'm going to also create a parameter that holds the image size we're going to create. So I'm going to go back up to my transform where I'm setting the image size. Make this a little bit easier to read. So instead of having it be just a number I'm pumping in, I'm going to create a variable that holds the image size that we want to set things to. I'll make sure that that is in my transform. And that way, when I load my image here, if I change my image size there, the transform will also match the CNN. And the number of classes that we are predicting is equal to the length of my data set ID to labels. And for now, we'll leave again our hidden dimensions to be the default. And I'm also going to remember this time to move it directly to my GPU. And let's run this cell. And I need to define that image. So I can do another nice thing that these cells have is I can click run above, and it will run all of the cells from top to bottom above this. So now I rerun those, and image size should be defined. And I run that, instantiate our model, and I see that the intermediate output, this is again from our initializer, the shape here, where I'm printing the shape of the output of my CNN block. I'm seeing that it comes out as 256, and it is a 128 by 128. This was one batch, and I can see my architecture. My flatten layer is appropriate, and we are good to go. Well, okay, let's implement our training loop. So first thing we'll define is our learning rate, which we'll set to 1 equals -3, and our max epochs equal to 100 again. We'll use cross entropy. We'll use the Atom optimizer again, setting our model parameters and our learning rate to learning rate. Now this time, instead of implementing the training loop from scratch, I have already implemented a helper function that will do the training loop for us and return the training curves and the validation curves. And epsilon, this epsilon is the same as that min delta. I'll just set it here to be explicit. And the device that we're working on. And the final thing I need is the loss function. I'll keep that in the right order. And now we'll begin training. Training has stopped at epoch 12, so we've converged. So let's bring in some of our analysis code here. And in this case, I have our loss curves in train curves and val curves, where train curves is just a list of training losses, and val curves is a list of tuples of validation accuracy as well as the loss. So I get both. So the first thing I'll do is kind of unwrap that accuracy, and here with our first attempt, training finished. We see that early stopping happened after epoch 10, or at epoch 10. And I can notice a couple quick things just by looking at the output here, is that the accuracy never really got above 30% or so, and the loss didn't seem to improve that much throughout training. So it's very likely that we have some problems. But let's take a look at our training curves. to verify that. So I'm bringing in some extra code here to just quickly plot our training curves. The train curves variable holds just a list of the training losses, while as the val curves holds a list of tuples of the accuracy and validation loss. So I'm just iterating through those val curves to pull out the accuracy and validation so that I can separate them, put them in different plots, and then I'm plotting them. So we'll do a quick plot here, and we can see that, yeah, something's off. Our training curves don't look right. We're not really learning. We're sort of plateauing very, very quickly. And one of the potential things that could be is that our model is actually pretty big. We have a fairly small data set. We don't have tens of thousands of images. We only have around 3,000 images. So we might have a model capacity that is much, much larger, and that would require much more data in order for it to learn anything. So the first thing we can try is to reduce the size of our parameters, or the size of our model. So I'll come up here, and instead of changing the defaults, I'll change it in our initializer. And let's set the HDIMS to 128, 256. Let's start with that. So this will be our first iteration to try to improve the model. I'll rerun my class definition, and I will also rerun training. After a second training run with a smaller model, interestingly, we can see that the accuracy did bump up to around 76 or so. So let's take a look at those training curves. And we see that we did get somewhat of an improvement, right? We actually seem to be learning something. Our accuracy was around 70%, kind of danced around there. Let's do from part one, let's grab our code for the analysis. We'll grab our confusion matrix code and score distributions. And I think I might need to update some things. Loaders. So because I'm using the training helper, instead of just saving it as best, it's saving it as the name of the class, best, and then a timestamp so that I'm not always overriding the previous training run. I will also, instead of just loading the raw, I will actually do another rglob. So I can do model root.rglob, and I can get the ETH models, right? I will sort that. I can grab the last entry, which should be my most recent training. I might have some parenthesis issues. This might need to be a list first. We'll add the TQDM. Run that top cell again. There we go. So if we look at our overall accuracy of this model, we are around 70%. That was about the best we could do. And this is the accuracy on the test split. So we can see the diagonal is kind of predicting okay on the contact layer, but really struggles as we get to the other layers. So another thing we can try is introducing max pooling layers, which is a common tool, a common layer that is used in convolutional layers. It is a way to also not only improve performance, it can improve performance at times, but it can also reduce the number of parameters you have in your model, even with more layers. So if we change our architecture to add a max pool layer after the ReLU, if we add a max pool 2D, and we set the kernel size to 3.3, say 2.2 is probably better. Keep these 2.2 as well. So now, instead of just the output of the ReLU, we will have a max pooling output. The max pool actually will reduce the size of our output. So we're going to add a couple extra layers. Again, we'll add back our 128 and 256 layers. So I'll go back to the default model, and rerun and see if we can further improve this or if this is a step in the wrong direction. And when I run that, I notice that instead of outputting 256, 128 by 128, I greatly reduced the size of sort of those images that I'm outputting in the intermediate CNN block down to just 8 by 8 small images for prediction. So we're hoping that sort of these max pooling layers are summarizing the statistics as the image is moving through our convolutional layer. And then we're looking for maximum response values from the kernels. And we'll run training again. So in this, after the third training run finished up, I early stopped at around 24 epochs. And I can see that the validation accuracy jumped up to around 98% this time. So take a look at the validation curves and see that the model started to learn fairly quickly, or it learned quickly at the beginning and then leveled out and started to converge. And it took much fewer epochs to jump above 95% accuracy, left side being loss, right side being accuracy in these plots. And let's continue to the confusion matrix. And I can see that the overall accuracy on the test split is around 96%, with some issues here and there. And then we'll look at our score distributions. Now we can look at our score distributions. And we can see that the model tends to be fairly confident as to the predictions it's making. And there's one last thing that we can try, or actually quite a few things we can try, but one last thing we will try is data augmentation. So we have a small data set. Can we augment this? Can we introduce transforms of our images to improve the model's ability to generalize? So right now we're getting around 96% test accuracy. So let's see if we can introduce some data augmentation to improve this model's ability to generalize. One final modification to our script we can make to potentially improve performance is data augmentation, where we can take our small data set and create variations of that small data set to increase the data set size, and also see if that helps us to improve the model's ability to generalize our task. So the first thing I'm going to do is update my transforms input to version 2, update in an updated version to version 2, an updated version of the transforms package from Torch Vision, which it's a little bit faster, has some more features and functionality. And then I will create a separate transform for my training split that performs these augmentations. So I'll keep this transform for the test and validation splits, but I'll update my training split to a new separate augmentation transform. With the version 2 transform, there are some slightly different function calls here. First, I'm turning it to an image data type within the transforms package, randomly horizontally flipping it, randomly vertical flipping it, and randomly applying an auto contrast. There are other transformations you can select. We'll start with these. And then finally, I am just returning that data type to a torch tensor float 32. Next, I need to update my dataset class to use this transform. So I'll go down to where we initialize our dataset, and I will use the train transform function if the split is equal to train. Else I will use the default transform that we already had. The other thing that I'm going to do is add an augments flag to a Boolean flag to the dataset if the split is equal to train. So the augments flag will be true when the split is training. Go to my initializer, and I'll add this augments flag. And how I will use this is in my len function. I'm going to, when I'm augmenting, I'm actually going to return, say, 4 or 5 times the number of files I actually have. So if self.augments, I'll return len of self.image files times 5. So I'll have 5 extra samples per image. Because returning the multiple of the actual number of image files, the indexes I'll be given in the getItem function will actually be in that space, right? Instead of having 0 to 10 or 0 to 9, it'll be 5 times that. So in order to return it to the appropriate index space, if self.augments, if I'm returning that larger number, I need to update the index to be the integer index divided by 5. So I'm bringing that index back into the appropriate range for my image files. And this will obviously, each image will be seen 5 times because I'll see that multiple of the image files. And I will use that transform, which should create variations each time that transform is applied. And with that, I should have an augmented data set, and I can rerun our training pipeline. I will go to the bottom of our script, return to the training cell, and I'll just click here where we'll run above our training loop to trigger everything all the way down to right before we plot our curves. I forgot a comma. We'll do the same thing. And one last thing I forgot to do is to still resize our images to the appropriate image size. After training with our augmented data set, we early stopped at around epoch 11. And let's take a look directly at our confusion matrix and look at our accuracy on the test data set and see if we gained anything. With our augmented data, it seems that we were able to squeeze out another % of accuracy on the test data set. So it did improve a little bit our model's ability to generalize the test split, but we didn't necessarily explore the full spectrum of augmentations. We can do more cropping, we can add more noise to the images, we can do a lot more augmentations that may further improve this. And this process of iterating with different hyperparameters and trying to see if we can improve our data set, the quality of our data set, is the process of refining these models. In the second part of our series, our deep learning series, we implemented a custom data set to load our SEM images. So we were able to implement that and load them and have more control over how we're loading the images. We refactored our CNN. We also looked at ways of improving performance of our classification task by modifying the size of our model, either through changing the layers, how many layers we've implemented, or the architecture design, as well as adding max pooling layers, which also reduced the number of parameters in our model and how that relates to the data set size. So just because we had a much smaller data set than we saw in our first part, where the CFAR data set had tens of thousands of images, we only had on the order of around 3,000, but we were able to get decent performance with a smaller model as opposed to a larger model. And then we also saw how we could introduce data augmentation to our data set pipeline to improve performance for generalization, where we could create more variations of our small data set and squeeze in a little bit of extra performance out of our model on the test data set split. So thank you, and I hope you enjoyed this.